Hello everybody, this is Mr. Woodward. In this video, we're going to apply the work-energy relationship, sometimes called the work-energy theorem, to an example of a rocket-propelled car. And we're going to see how the conservation of energy and the application of work explains the motion of the car. So let's take a look at this example together. A 350 kilogram rocket car is attempting to beat the land speed record by breaking the sound barrier, which means reaching a velocity of 343 meters per second. That is the speed of sound in air. The rocket applies a constant horizontal thrust of 10,000 newtons, which I can add to the picture, saying that there's this thrust of 10,000 newtons. For the purposes of this problem, we can neglect air resistance and friction. Okay, so in a previous lecture, I introduced the idea of a work energy bar chart to try to stay organized with how work and energy are relating to each other. And so taking a look here at part A, use the bar chart below to diagram the work energy relationship in this situation. Assume the rocket car starts from rest. Okay, so we're saying V initial is 0. Be sure to carefully define the initial and the final states for the rocket. Okay, so over here on the left side is the initial state. And over on the right side is the final state. And in between the states, what brings the object from the initial to the final state is usually some work that's done. Okay? And just a reminder real quick that in physics, we define work as the product of force and distance. Okay, force and distance. So let's first start with this initial state. I'm going to define the initial state as this moment when the car is at rest, okay, and it's on the ground. So in this initial state, if it's at rest, it has no kinetic energy. So I can just put a line here to remind myself that there's no kinetic energy. And if it's on the ground, it has no height. So it also has no potential energy, okay? So no energy of any kind in the initial states. And then in the final state, we see that it's being pushed forward, and so it's going to accelerate to this 343 meters per second, okay? So in the final state, it's moving quite fast. It's got a lot of kinetic energy, and so I'm just going to fill this all the way up. But it's still on the ground. It hasn't gained any height, so its potential energy in the final state is still 0, okay? And so now if we're looking at this relationship, what we're seeing is that we're going from an initial state of nothing, right? No energy, to now a final state of having energy. And so where did this energy come from? Well, it came from work. Work was done, and work was done in the form of this force of thrust on this rocket, on the rocket car, okay? And so that force applied over a distance produced work. And so I'm just going to add to my work column this, and we call this positive work, by the way, because it's energizing the car. Negative work is when the object loses energy. And so now you can see that there's this conservation of energy, right? On the left side, we have 5 bars of energy altogether. And on the right side, we have 5 bars of energy. And so the energies are being balanced. Okay, so this is conceptually how work and energy are relating to each other. Now let's add some calculations. So question B, it says calculate the work done to the rocket by the thrust force and assume that it's being applied over a distance of 100 meters. Okay, so going back to that definition of work that I gave you, it's the force times the distance. So we have 10,000 newtons of force applied over a distance of 100 meters. That's equal to 1,000,000 joules. A million joules. Continuing on, use your answer to part A, and I actually think it's referring to this part, to determine the speed of the rocket car after it has traveled a distance of 100 meters and assume it began at rest. Okay, so what I'm going to do now is I'm going to take this idea here, that the initial energy plus the work that's done is going to be equal to the final energy, and I'm going to apply that, okay? So the initial energy is the sum of the potential plus the kinetic, that's the initial energy, plus any work done will be equal to the final energy. Okay, the final total energy is the sum of potential and kinetic. Okay, well, we know that the initial potential energy was 0 because it was on the ground. We know that the initial kinetic energy was 0 because it was at rest. And then we know that we're adding 1,000,000 joules of work to this system, okay? And I'm going to use the shorthand. 1 times 10 to the 6th joules is scientific notation, right, for 1,000,000. And then I'm going to set this equal to the final potential energy plus the final kinetic energy. Well, in the final state, the car is still on the ground, so it is going to have no gravitational potential energy, but it will have some kinetic energy. And kinetic energy is 1/2 mv squared. Okay, so now you can see where I'm going to be able to get the speed, right? It's going to come from this velocity term. So simplifying this, I can see that 1 times 10 to the 6th joules is going to be equal to 1/2. The mass of the car was given to me up at the top. It's right here, 350 kilograms. And then the velocity is my unknown. So doing the algebra, right, multiplying both sides by 2, dividing both sides by 350, and then taking the square roots, I get that the velocity is going to be 75.6 meters per second. Okay, and by the way, that's roughly 150 miles an hour. So the car gains that much speed in only 100 meters. All right, closing this out. What horizontal distance would the rocket car need to get up to the speed of sound if it's starting from rest? Okay, so speed of sound, this was given in the introduction. I'm going to say this is the final velocity, 345 meters per second. That's the speed of sound. Okay, so what horizontal distance would be needed? So I'm going to grab this same statement and use it again down here. Okay, so the initial potential energy plus the initial kinetic energy plus any work done is going to be equal to the final potential energy plus the final kinetic energy. Okay. The rocket car is still going to be on the ground this whole process. So the initial potential is 0. The final potential is 0. It's still starting from rest, right? There it is, starting from rest. So the initial kinetic is still going to be 0. And then I'm going to break apart the definition of work, right? Work is force times distance. So there's my work term. And then I'm going to add the final kinetic energy, 1/2 the mass, which is 350 kilograms, times now I have this new final velocity of 345 meters per second, squared on the outside, 1/2 mv squared. Okay, and so you can see where I'm going with this. It says what horizontal distance, right? So I need to solve for this distance here. And so I know the force. The force is actually, I'm going to break apart this part. The force is 10,000 newtons times some distance is going to be equal to 1/2 times 350 times 345 squared. And let me just get that real quick. That's a massive number, millions of joules here. 20,829,375 joules, okay? So dividing both sides by 10,000 gives me a distance of 2 2,083 meters. I'm rounding that. 2,083 meters. And I just realized that I actually copied the speed of sound incorrectly. It's 343 meters per second. My bad. Let me fix that. So this is going to go in here. 343. This is now slightly different. $20,588, 575 joules. And so this is now 20,059. All right, so that is how you can use the work-energy relationship to solve problems involving force, distance, velocity, and different levels of energy.